Yeah, hello everyone, I'm Kisor Lee from Cornell University. Today I'm going to talk about a new type of cover timing channels which is implemented in the physical layer of network protocol stack. Our channel is high bandwidth, robust against network noise, and invisible to software. This is a joint work with Wang and Professor Hakim Weatherspoon. Our system is called Chupja, which means spy in Korean language. And throughout the long history of Korea, there have been a lot of spy activities. Interestingly, it is known that the activity of spies was most frequent during the 7th century because of the wars between three kingdoms in Korea. They were trying to unite the kingdoms by sending a lot of spies, basically. Similarly, the United States have a rich history of spies. For example, George Washington is known as the spy master of a secret group called Culper Ring. And throughout the World Wars and Cold War, and even nowadays, we know that there are a lot of spies out there gathering information. So in the same way, covert channels are trying to hide their existence, and they hide the information through the channels that are not intended for data transfer. Because covert channels can leak information, they can be a serious threat to system security. If covert channels use packets to deliver hidden messages, we call it network covert channels. And there are generally two different types of covert channels. If the sender modulates bits or some values of the packet headers, we call them storage channels. And if the sender modulates the timings of packets to embed the messages, then we call them timing channels. And the focus of this talk is the timing channels. And there are generally three different goals while implementing covert timing channels. One is bandwidth, which is to send as many bits possible per second. And it must be send those bits without errors or without loss. And it must hide itself from other entities of the system. And there have been a lot of works implementing covert timing channels in the network. And most of them are trying to limit their bandwidth to be more robust and more undetectable. So very simple IP timing channels try to send only tens or 100 bits per second to achieve the robustness. But these simple timing channels can create some patterns of timings of packets, which can be later analyzed by statistical tests to detect any potential existence of covert timing channels. So in order to be more undetectable, people have tried to make the covert timing channels make more look random or make them more look a real traffic. But the thing I want to say about these covert timing channels is that they are normally implemented in layer 3 or 4 network protocol stack. So they are relatively easy to create, and also they are relatively easy to be detected by software. So the takeaway is that current network covert channels are implemented in higher network layers protocol. So they operate at very extremely slow data rate to achieve the robustness and detectability. But in this talk, I'm going to introduce Chupja, which is the new type of covert timing channel, and try to achieve all of these goals. And the key that we can achieve all of these goals is to access the physical layer. So by implementing these covert timing channels in the physical layer, we can send tens and 100 kilobits per second, which is orders of magnitude of faster than the other covert timing channels. And you can effectively deliver those bits over multiple household routers with a bit error rate less than 10%, which can be easily compensated by forward error correction. And also it's invisible to detection software. So again, Chupja, our physical layer covert timing channel, is implemented in the layer 1 of the network protocol stack, and which is highly faster than other approaches and very highly robust and virtually invisible to software detection programs. So for the rest of the talk, I'm going to talk about the design and evaluation of the system. And before going into the details of the design, I'm going to show you our threat model and how 10 gigabit Ethernet protocol operates. So in our threat model, we assume that the sender and the receiver may or may not be in the same network, and the sender tries to modulate the timings of packets to send hidden messages. We assume that the sender and the receiver, both they can access the physical layer of the network protocol stack. And there's another entity called as adversary who is trying to detect the possibility of existence of covert timing channels. We assume that it's passive. That means it does not employ any network devices such as network jammers to reduce the possibility of covert timing channels. Instead, it simply looks at timings of packets to analyze the potential existence of covert timing channels. We further assume that the adversary is using commodity servers and commodity network interface card to analyze interpacket delays or timings of packets. And the key feature of 10 gigabit Ethernet protocol that allows us to implement this Chupja is idle characters. Idle characters are special characters that only reside in the physical layer of a network protocol stack. And they are essentially the characters that fit between any two Ethernet frames in the physical layer, so that each end can send 10 gigabits per second. Because each end sends 10 gigabits per second, each bit is about 100 picosecond wide. And one idle character consists of 7 to 8 bits. So it takes about 700 and 800 picoseconds to deliver one idle character. So by accessing the physical layer, we can modulate timings of packets at sub-microsecond scale to create a timing channel. Let me define a few terms before I move on. Interpacket delay is defined as the timing difference between the first bit of two subsequent packets, and interpacket gap is defined as the timing difference between the last bit of one packet and the first bit of the next packet. And we define a homogeneous packet stream where the packets in the stream have the same destination, same packet size, and same interpacket gap. Because those packets have the same packet size and same interpacket gap, naturally interpacket delays are also same between these packets. As a result, the variance of packet size and interpacket delays or interpacket gaps are always zero in a homogeneous packet stream. So given a homogeneous packet stream, the design of Chupja is very simple. So given that the interpacket gap denoted as G and interpacket delay denoted as D, the sender simply add or subtract some number of idle characters, we call epsilon number of idle characters, to embed messages. And as interpacket gaps will be perturbed by the network noise of the multiple hops of routers, the receiver can just simply count the number of idle characters to decode messages out of it. So to be more specific, assuming that the sender and the receiver shares original interpacket gap G or original interpacket delay D, the sender can encode signal 1 by adding epsilon number of idle characters. In the same way, the sender can encode signal 0 by subtracting epsilon number of idle characters. And these interpacket gaps will be significantly perturbed by the network, and the receiver now can simply decode messages by counting the number of idle characters. And if it is larger than G, then it's signal 1. And if it's smaller than G, then it's signal 0. So the design of Chupja is very simple. But we need to access the physical layer to implement this covert timing channel. So we use SONIC, a software-defined network interface card, which I presented last year. SONIC basically allows users to access and control every single bit in transit of the physical layer in real time and in software. So this is a perfect fit to create this timing channel. And we only added less than 50 lines of C code on top of SONIC implementation. So, as I mentioned in the beginning of this talk, there are three general goals of covert timing channels: bandwidth and robustness and undetectability. And I'm going to show you how Chupja performs on these metrics. And I'm also going to spend some time on why is Chupja working in practice. So first of all, what is the bandwidth of Chupja, or the physical layer covert timing channel? Because we are embedding 1 bit per 1 interpacket gap, the data rate of this covert timing channel equals to the packet rate of over channel. So given a packet size and the data rate of over channel, we can compute the maximum capacity of this timing channel. So in this graph, x-axis is the throughput of over channel, starting from 10 megabits per second up to 9 gigabits per second. And y-axis is the maximum capacity of covert timing channel in bits per second. And with this small package, like 64-byte package, we can easily embed millions bits per second with this channel. But as we increase the size of the package, we can embed less and less bits per second. But still, with the MTU, or maximum transmission unit size package, we can embed tens or 100 kilobits per second with sufficiently fast data rate. For example, a stream with 15, 18-byte package running at 1 gigabit per second, we can embed 81 kilobits per second. So throughout the rest of talk, I'm going to this stream to evaluate other metrics. So again, the bandwidth of our covert timing channel is equal to the packet rate of our channel. Then how robust is Chupja? So we use bit error rate to evaluate the robustness of our system. Bit error rate is defined as the ratio between the number of bits correctly delivered to the receiver and the total number of bits generated by the sender. And in order to evaluate robustness, we use two networks. One is small network in our lab, which consists of 6 commercial switches. The average round trip time was 1/5 of milliseconds. And we also tested against National Lambda Rail, which is experimental network, a research network which spans across the United States. So we created 9 routing hubs in the network, and average round trip time of the network was 67 milliseconds. And there were consistently about 1 to 2 gigabits per second external traffic that we do not have any control over. So we are interested in the optimal number of idle characters that we can modulate to achieve the goal bit error rate less than 10%. So as I said, we are using the stream running at 1 gigabits per second with the 1518 byte package. And the bandwidth of this channel is 81 kilobits per second. And in this graph, we modulate the number of idle characters from 16 to 4,000, as is shown in the x-axis in the graph, and y-axis is the bit error rate. And the purple line in the middle is the target goal, bit error rate, 10%. So first of all, within the small network, when there is no external traffic, we can easily achieve the goal bit error rate less than 10% by simply adding 128 idle characters or subtracting 128 idle characters from the original interpacket gap. Even with the existence of external traffic, which is running at 3.6 gigabits per second, now we need to modulate more and more idle characters, but if we modulate 2,000 idle characters, we can achieve the bit error rate 2.8%. Similarly, in National Lambda Rail, where we do not have any control over external traffic, we can still achieve the same, we can achieve the bit error rate less than 10% by modulating about 2,000 idle characters. So the takeaway here is that by simply modulating interpacket gaps at 1.6 microsecond scale, or about 2,000 idle characters, we can effectively construct the cover timing channels of a real network with the existence of external traffic. Then why is Chupja robust? Our expectation is that small interpacket gaps will be perturbed by the network noise. Then how can those interpacket gaps will be preserved along the path of the network? So in order to show you how this works, I'm going to make these observations for the following few slides. And I'm going to generate a homogeneous packet stream running at 1 gigabit per second first. And I'm going to use the Chupja stream, where I modulated 256 idle characters to deliver hidden messages. So first of all, switches do not add significant perturbations to interpacket delays or interpacket gaps when there is no external traffic. So here the graph on the left is how interpacket delays are changing after one hop or after switches of a homogeneous stream. The red vertical line in this graph is the original interpacket gap of a homogeneous stream. So after one hop, this is how interpacket delays are now changed. Originally, all the interpacket delays of this stream was in the red vertical line, but now it's perturbed and spread across the different interpacket delay values. But still, more than 90% of interpacket delays are within the range of 100 nanoseconds from the original interpacket gap or interpacket delay. Then now, what's going to happen to a Chupja stream? Because a Chupja only add or subtract some number of idle characters, there are going to be 2 distinctive interpacket delays that leave the sender, namely D plus epsilon idle characters or D minus epsilon idle characters. And they are shown in 2 vertical lines on the right graph. And after one hop, this is how interpacket delays are changed. The lines on red are the interpacket delays of signal 0, and the line in green are interpacket delays of signal 1. And please note that the similarity of the shape of these distributions of 0 and 1 to the one from the homogeneous packet stream. They look very similar. Moreover, the perturbations added to this distribution is also similar to that of homogeneous packet stream, which is 100 nanosecond. And this happens across multiple hops of routers when there's no external traffic. So if we increase number of hops of routers to 3 hops, 6 hops, or 9, 12, and 15 hops of routers, we can still see that the distributions look very similar to that of homogeneous packet stream. And interestingly, more than 90% of interpacket delays are still within 250 nanoseconds from the original interpacket delay. Please note that the y-axis is in log scale, not in a regular scale. So the takeaway is that if we modulate enough number of idle characters, which is larger than the range where more than 90% of interpacket delays are, then we can effectively construct the cover timing channels that can achieve bit error rate less than 10%. Then what happens if there are external traffic? So even if there exists external traffic, that still holds true. So we test against National Lambda Rail again, and we captured how interpacket delays are changing because there were consistently 1 to 2 gigabits per second external traffic across the National Lambda Rail. And I'm going to show you how the distributions of signal 0 and 1s are changing in the relation with the number of idle characters we modulate. So this is how it looks when you modulate simply 256 idle characters. As you can see, the distributions of 0 and 1 in red and green are clearly overlapping altogether, making bit error ratio less than quite high, about 36%. But if we increase the number of idle characters that we modulate more and more, then the distributions of 0 and 1s will be further apart from the original interpacket gap, making us to achieve the bit error rate less than 10% by simply modulating more than 2,000 idle characters. And if we modulate about 4,000 idle characters, we can even achieve bit error rate less than 1%, like 1.3%. So the takeaway here is that with sufficiently large epsilon, or the number of idle characters that we can modulate through the Chupja, the interpacket spacing holds throughout the network of the multiple household routers, even with the existence of external traffic, and still allows us to achieve the bit error rate less than 10%. So you might think that modulating 4,000 idle characters is quite large to be detected by software and host, but it turns out to be not. So in order to show you that Chupja is undetectable, we use commodity server and commodity network interface, which uses kernel timestamping to see if we can see the patterns of cover timing channels. So with the same setup, after the National Lambda Rail, we plug the cable into one of the commodity server and enable kernel timestamping to capture the interpacket delays. And with the exact same setup, we instead use USENIX to capture the timestamping if we can see the patterns of cover timing channels. So here I show you two graphs. One on the left is by kernel timestamping, one on the right is by USENIX timestamping. And here x-axis is the interpacket delays in nanosecond, and y-axis is the PDF in log scale. In both graphs, the red vertical line in the middle is the original interpacket gap that we modulate to create cover timing channels. So first of all, when you send a homogeneous packet stream, this is how interpacket delays look like by kernel timestamping. Please note that most of interpacket delays are now a very small number, which is very close to the minimum interpacket delays allowed by standard. And the reason of this is because the batching between the network interface code and the kernel space. If we send a Chupja stream by modulating 1,000 idle characters, or about 800 nanoseconds, we can see that the patterns of interpacket delays look very similar to that of homogeneous packet stream. And even if we modulate 4,000 idle characters, the kernel is not still able to differentiate those streams just by looking at interpacket delays. On the other hand, using sonic timestamping or hardware timestamping, we can easily see that those patterns look different by modulating more and more idle characters. So the takeaway here is that adversary who is using commodity servers or commodity network interface cards is not able to detect any patterns out of Chupja by simply looking at interpacket delays. So if the adversary does not have enough fidelity to accurately timestamp incoming package, they are not able to detect Chupja. So in this evaluation section, I show you that system can stand tens of or hundreds kilobits per second, effectively over the real network with the existence of covered external traffic that we can achieve bit error rate less than 10%. And we show you that sufficiently large epsilon number of idle characters allows us to achieve these goals. And also show you that our system is invisible to software detection programs. So to conclude, I introduced Chupja, a new type of cover timing channel which is implement the physical layer, which is high bandwidth, robust against network noise, and undetectable. And our system is working because it's based on the understanding of how network devices behaviors. And we also exploit the fact that kernel timestamping is highly inaccurate in 10 gigabit Ethernet standard. Sonic and our Chupja is available in this website and is now integrated into Genie, especially in Exogenie Rack, so you can provision Sonic servers to test on yourself. And also we have a poster session today, so if you are interested, you can come and discuss about it. Thank you, and I'll take questions.
Hi, Dong-Soo Han from KAIST. I have 2 questions. So since you're doing a covert channel, the overt channel's message must look innocent, right? Otherwise, it would raise suspicion, and it could easily nullify the covert channel because it's timing-based, right?
Yes.
Do you have any answers to those?
So in this evaluation, we use sender and the receiver as an end host in the network, but actually we can deploy our system as a middle box basis. In that case, we can use any other applications package from other end hosts too, and we can just modulate interpacket gaps to deliver hidden messages.
Okay. My second question is, have you considered rate adaptation, basically adjust the value of E based on the path that you observe?
So in this work, we just basically show you that this very simple timing channel can efficiently work with just modulating enough number of idle characters. But basically, you can apply any other schemes by making epsilon values random or making IID. You can apply all of these techniques to these simple timing channels to make it more random or make it more robust.
Thanks.
Okay, thank you.